Looking a little silly there. All right. Good morning, guys. I'm going to go ahead and close my office door here, and we can get started. Annie, come here, baby. Come on in. I don't want you to be sad. Come on. Good boy. Yes, I love you. You're very sweet, very handsome. All right, let's do this. So, welcome to the last week. There's not a lot left to cover, but I want to describe to you guys a little bit kind of how I've combined the final homework and study guide, and then we can get started talking about the last little bit of material here. I lost him, didn't I? There he is. All right. So the final homework and final study guide. Screw it. Your tie broke. The final homework and final study guide are going to be the same assignment in WebAssign. The idea here being that rather than giving you two separate assignments where you've got extra stuff to do, because the homework really, has to contain certain problems, and the study guide really has to contain certain problems, or at least problem types, I would be overloading you if I gave you two separate things here. So the study guide for the exam 3, which is the last study guide for the class, is the same assignment as the last homework for the class. And that's up now. It contains all the stuff you would expect it to contain, everything that we've talked about since exam 2. So there's some power series questions, but not a lot. There's some arc length and surface area questions, but not a lot. And then there are some parametric curves and polar coordinates questions, but not a lot. So I don't want to overwhelm, but I do want to make sure I'm giving you enough stuff to chew on to get good practice. Now, if you want more practice, I'm leaning towards less questions because, again, I don't want to overwhelm. But if you want more practice, of course, there's the textbook you can go into and solve more problems from. So don't treat the homework assignment that's up there as the only thing you can do. I don't think there's anything else that really requires a lot of explaining. So let me launch QCam and we can get moving. Our last topic for the class is polar coordinates, which is something that you should have seen a little bit of back in your trigonometry class. But as with all things, I know I can't really depend on you having seen this in your trig class. And even if I can't really depend on it having been rigorous or good. So let's begin at the beginning. This, there we go. All right. Ooh. Come on, Doc Cam. There you go. Wake up. All right. Okay, so today we're going to talk about section 10.3 on polar coordinates. This really doesn't like me. Come on. Focus, you fuck. So there's more than one way to describe the polar coordinate system. And this is a lot easier to do if we're sitting in a classroom, because I can be like, you would turn so far and walk so far to get from someone to someone. But I'm going to do my best to recreate my normal polar coordinate spiel here. So, maybe Bob is here and maybe Alice is here. Okay, and at the moment, they're both facing forwards. Like, let's say they're both facing this way. If I want to tell Alice how to get from where she is to Bob. If you're a fan of the Cartesian coordinate system, that is the system that we've been using all semester and the system you pretty much exclusively use in algebra classes, I would tell Alice to come, forwards like 3 feet and then to her right like 10 feet. But that's not how anybody gives directions. It's very rare that anybody gives directions that way. You would tell Alice, oh, well, turn 60 degrees to your right and then walk 8 feet. That's the difference between the polar coordinate system and the Cartesian coordinate system. We have two options. Let's suppose this is the north. All right. Then we could say, using the Cartesian coordinate system, walk south like 5 feet, then walk west, what did we say, 10 feet. All right, and that's laying out this rectangular path that Alice could take to get to Bob. Or, and this is kind of the polar way of thinking, I could tell her, rotate some amount and then walk over here. So I could say rotate whatever this is, I don't know, 45 degrees. Rotate 45 degrees to your right. Then walk 8 feet. The idea is this: what is a coordinate system? A coordinate system is a means of locating points in space. The Cartesian coordinate system does that by specifying a horizontal position and a vertical position. The polar coordinate system does that by specifying an angle and a distance. Both mechanisms will allow you to get from one place to another, or equivalently, describe any point in space. Strictly speaking, what are polar coordinates? We want to be a little bit more concrete about it. The Cartesian point x, y, this is your y-axis, this is your x-axis. Can be thought of as going over this far and then up this far, or can be equivalently thought of as rotating up this angle and then walking out this distance. The distance we call r, the angle we call theta. And what you'll notice is that there's a nice relationship that one can construct between x, y, r, and theta, owing to the fact that this is a little right triangle. Now this should be coming all the way into the origin. My art is just bad. So if you look at this right triangle, then this side length right here, which is y, you'll see is equal to well, let's look at it like this. The sine of theta, put it down here. The sine of theta is equal to the opposite over the hypotenuse, which means that y is equal to r sine theta, and the cos of theta is the adjacent over the hypotenuse. That's x over r, which means x is r cos theta. And then the last sort of nice thing to observe here is that x squared plus y squared has to be r squared. And the tangent of theta is y over x. So these things, these are sort of your Bible to go back and forth, or your key, or your dictionary to go back and forth. You have these two, and these two, which are your key to going back and forth from polar coordinates to Cartesian coordinates. Okay, any questions so far? Is any of this new to anybody? Anybody not see this in their trigonometry class? I found another hair tie here. So what is new is that we're going to want to do calculus in this polar setting, which means first we need to learn how to graph functions, which means first we need to learn how to graph points. So we're going to talk about graphing some points, going back and forth polar to Cartesian. Then we're going to do that for a whole bunch of points at once, specifically the points on the graph of a function. And then we'll look at some functions in polar coordinates, and then we'll do some calculus there. Okay, so let's express the Cartesian part uh, 2, 2 in polar coordinates. Okay. So all right. Here's your Cartesian point 2, 2. I would like to find r and theta. So just for the record, sorry, we always write r first. This is a slightly weird choice of notation. It can be frustrating sometimes because usually when we're thinking of these as functions, we write the independent variable first, but r is the dependent variable. Still, you write r first, and you can think of this as living on a circle of radius r. So you like walk out r units, and then you rotate up theta. But the point is always read as r comma theta. All right. So let's express this Cartesian coordinate point 2, 2 in polar coordinates as r comma theta. What do I do? We said that these items here are the key to going back and forth. Is there one of these things that can help me figure out r? Is there one of these things that can help me figure out theta if I know x and y? Good. Yeah, we know that r squared is x squared plus y squared. So here, r squared is x squared plus y squared, means r squared is 2 squared plus 2 squared, which is 4 plus 4. which is 8. So r squared equals 8. So r has to be the square root of 8, which is the same as 2 square roots of 2, because 8 is 2 times 4. Okay, so I've got r. What about theta? Is there a nice way to get theta? Yeah, and we have to be a little bit careful here. So I'll always write this as tangent theta equals y over x. Usually the way you'll find theta is by taking the inverse tangent of both sides, but you do have to be a little careful because arctan will only ever output numbers that are between negative pi over 2 and pi over 2. In other words, arctan will only ever give you angles between here and here. So if you've got a point in quadrants 2 or 3, you'll need to be a little bit careful with the inverse tangent function. But here we know tangent of theta is equal to y over x. So tan theta is equal to 2 over 2, which is 1. So theta is the inverse tangent of 1, which is pi over 4. Okay, so this r here, this radius, this distance from the origin is 2 root 2, and this angle in here is pi over 4. In other words, that point as a polar point, the polar coordinates for that point, r comma theta, would be 2 root 2 comma pi over 4. And remember, it's always r comma theta. These guys are the same. All right, let's try one or two more. Any questions on this? All right, let's try one or two more. Move a little faster. Let's take something that's outside of the right half plane. So let's convert the Cartesian point negative square root of 3 comma 1 into polar coordinates. I can plot the point. I recommend you do this. Drawing the picture is usually helpful. Never hurts. All right, so here it is. And the same sort of thing works great. R squared is still x squared plus y squared. So that's negative square root of 3 squared plus 1 squared, which is 3 plus 1, which is 4. So r is equal to 2. And we know that the tangent of theta is x over y. Y over x, which is 1 over negative square root 3. And this one might take a second if you don't remember your unit circle super well. You can divide top and bottom by 2. You can think of this as 1/2 over -√3/2. And that should help you recognize your theta value from the unit circle. Now, if you did this using the inverse tangent function, it would give you an angle over here. I want to make that clear. I'm not going to use the inverse tangent function here. This is one of the reasons why I said draw the picture. So, what angle in quadrant 2, when you take the tangent of it, will give you -1/√3, or what angle has y and x coordinates like this on the unit circle? Anybody? Anybody remember their unit circle well enough to tell me what angle theta gives me this y and this x? 150. Yeah, that's correct, but it's in degrees. What about in radians? Good, yeah, 5 pi over 6. So 150 degrees is correct, but remember in mathematics, we're always using radians, always using radians. So it's 5 pi over 6. Now, just for fun, I want to note the inverse tangent of this number is not that, right? It's negative pi over 6, which is not the same as, obviously, 5 pi over 6. So this is reason numero uno to always draw the picture, right? Really important that you have a geometric intuition for what's going on rather than sort of blindly following the algebra. If you were to take the inverse tangent on both sides, it would send you to the point over here. It would tell you that the angle is negative pi over 6 with a negative y value and a positive x value, because that's what the inverse tangent function does. It always sends you to an angle that's between negative pi over 2 and positive pi over 2. Arctan will always give you something between here and here. It'll never send you over to these quadrants. So you need to think critically about it. Okay. That's it. So oh shit. So this distance here is 2. That's r, and this angle here is 5 pi over 6. So the polar coordinates of this point are comma theta are 2 comma 5 pi over 6. All right, real quick, is there any other way to express this point in polar coordinates? Any other choices for r and theta which are correct? What if I added 2 pi to this theta value? Yeah, very good. So let's see. We could measure the angle negatively like this, right? Then that would be pi plus pi over 6, or 7 pi. So pi plus pi over 6. So another way to do this, I could say that this is 2 comma negative 7 pi over 6. Because this angle here, measured this way, this is negative 7 pi over 6. Or Or, yeah, or we could go all the way around again, right? We could say that this is 2 comma 5 pi over 6 plus 2 pi. Or 2 comma negative 7 pi over 6 plus 2 pi. Or blah, 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 blah. Right, there's infinitely many ways to characterize this point in polar coordinates. In fact, there's kind of 2 whole infinite families. This is just one of them. So one of the infinite families of polar coordinates that will get you to this point are these ones that we're describing here, where you're allowed to walk forwards or backwards, right? You're allowed to rotate in the positive direction around like this, or in the negative direction around like this. And you just add multiples of 2 pi. So these are all of the guys. This can be written as 2 comma 5 pi over 6 plus or minus 2k pi, where pi is any, k is any integer. All of these will get you to that point. But believe it or not, that's still not all of them. You can also do this with a negative r value, and the negative r value stuff is where it gets a little bit complicated. So, with r less than 0, as I'll give you just an example here, I could use negative 2 and negative pi over 6. Because when r is negative, we reflect through the origin, which is also sometimes called the pole. So the polar coordinate system is really thought of like this. There's this thing in the middle here called the pole. And there's this thing which is called the polar axis. Now you'll see me in class conflating this with the x-axis and the pole with the origin, because they really are the same thing. And the idea is you go out some r, and then you rotate up some theta, and that's how you get to your point, r comma theta. But we'll also think of this as the x-axis, and then we'll kind of think of there as being a y-axis here. So I'll use those two terms interchangeably, polar axis and x-axis, and pole and origin. So yeah, we can spin around as many times as we want, and we can go in the positive rotation direction or in the negative rotation direction, and that's all of these guys. The other way that polar coordinates can be non-unique, in other words, another way you can find a set of polar coordinates that get you to that point, is to think about r being negative. Normally you think of a radius as being a distance, it has to be positive. But in this setting, that's not the case. So if you want to know how to interpret a negative radius, I'm going to show you 2 ways to do it here. All right, so one option, how to get to r being less than 0. Let me do a specific example here. How about negative 1 comma pi over 3? Okay. So the way I like to think of it is you go to the point with the positive radius, in this case 1 comma pi over 3, then you reflect through the origin. The other way to do it is to think about walking out -1 rather than +1 and then doing your rotation. So here, I'll show you how I like to do it first. First, we go out a distance of 1, and then we rotate up pi over 3. So here, this angle. So this would be my point right there. Right? And I'll draw this as a solid line like we were before. So here's the polar point, +1 comma pi over 3. So to get to -1 comma pi over 3, I would then reflect through the origin. Okay, so this means that -1 comma pi over 3 is right here. Now there's another way to do this. And that is you could somehow, this doesn't jive with a lot of mathematicians because it doesn't fit in the kind of rigorous strict definition we like to use, but you could go out -1. You kind of go out in the backwards direction on the polar axis and then rotate around by pi over 3. And that'll get you there also. So notice I land at the same point here. Okay, just know that the second way of approaching this isn't considered entirely rigorous, but you bet your ass it works. So, you know, I'm not about to stop you from thinking about it that way if you want to. Remember, these are all polar coordinates, r comma theta. There's no x's or y's here. This is not x, this is not y. This is r, and this is theta. This is r and theta. This is r and theta. Any questions about how to interpret a negative radius? Feeling mostly comfy? So I could ask you for like 3 different ways of describing a given polar point. I could ask you for 2 ways with a positive radius and 1 way with a negative radius. Or I could ask you, you know, here's a Cartesian point, you know, 5 comma 7. Give me 4 different polar representations of that point, 2 with a positive radius and 2 with a negative radius. And we're all comfortable doing that? Okay. All right, so the next thing I'd like to talk about then is plotting functions in this polar coordinate system. Where's my clock? There it is, 8:34. All right, we're still doing good. So next thing we need to talk about is how to graph functions. And that's where things get a little bit trickier. But there are several functions that are very, very easy to graph, and I like starting with the constant ones. So graphing these tend to come in 2 different flavors. You're either given something like r is equal to f of theta, or theta is equal to like g of r, right? Either r is a function of theta or theta is a function of r. just like how you normally graph things in Cartesian system. Usually either y is a function of x or x is a function of y. The more common situation is this one, but we'll see both. Right. So my first example, constants. Like theta is equal to 5. So if I take all the polar points whose theta value is 5, and let me be silly here. How about 5 pi over 4? Let me use a value, a constant value there that's a little easier to work with. You can make a table of values. You know, you can make an r comma theta table. So here's r and here's theta. So if r is 0, theta is 5 pi over 4. If r is 1, then theta is 5 pi over 4. If r is 2, then theta is 5 pi over 4. If r is negative 1, theta is 5 pi over 4. Theta is always 5 pi over 4. It's a constant function. So no matter what you do with r, theta is always 5 pi over 4. So let's plot these polar points. Okay, the polar point 0 comma 5 pi over 4. R is 0, so we're still at the pole there. The polar point 1 comma 5 pi over 4, I go out 1. And then I need to rotate 5 pi over 4, so that's 1, 2, 3, 4, 5 pi over 4. So here's the polar point 1 comma 5 pi over 4. Uh, 2 comma 5 pi over 4, so I go out 1, 2, and then I rotate around 5 pi over 4. That's going to put me here. What about negative 1 comma 5 pi over 4? So I can go to 1 comma 5 pi over 4 and then reflect through the origin. That's one way to do it. Or I could come out here, negative 1, and then rotate around 5 pi over 4 like that. Either way, we get to negative 1, 5 pi over 4. What about negative 2? 5 pi over 4. Well, that would mean I take 2 comma 5 pi over 4 and I reflect it through the origin. All right, so if you take all these points, you imagine r is allowed to be any real number, then this is going to slowly fill out, right? You're going to end up with your graph is, sorry, this guy kind of wandered a little bit, didn't he? You're going to end up with your graph looking like this. Sorry, I don't know how that guy got so far over. Yeah. Your graph is going to look like this. It's a line through the origin. So theta equals a constant has graph looking like a line through the origin. Where the angle here is 5 pi over 4. The angle is whatever the angle specified. Okay, another interesting constant function How about r equals 3? So instead of letting theta be constant and fixed, let r be constant and fixed. Again, we can make a table of values, r comma theta. And I can think of theta as going from, you know, like maybe negative pi over 2, 0, pi over 2, pi. And I know that no matter what theta is, r is always 3. So I've got the following polar points, like negative 3 comma negative pi, 3 comma negative pi over 2. So I go 1, 2, 3, and then I swing around negative pi. That's going to land me here. All right, so 3 comma negative pi is right here. Similarly, 3 comma negative pi over 2, I go out 1, 2, 3, I rotate down pi over 2. Uh, 3 comma 0 is right here. 3 comma pi over 2, I come out 3 and I rotate up pi over 2, that's right here. 3 comma pi, that would be here again. What about 3 comma pi over 4? You know, you can, what does this look like if you had to guess just based on the points we have here? What if I add in 3 comma pi over 4? 3 comma 3 pi over 4. Yeah, it's a circle. 3 comma pi over 4 is right here. Hereabouts. 3 comma 3 pi over 4 is right here. It's a circle of radius 3 centered at the origin. R equals a constant is a circle centered at the origin of radius that constant. Remember, you can think of r as being the distance from the pole or the origin to your point. So if you're looking at all the points whose radius is equal to 3, that means you're looking at all the points whose distance from this center pole here is 3. That's the geometric definition of a circle. So yeah, it's a circle. R equals 5 would be a circle of radius 5 centered at the origin. What about r equals negative 6? Right, so fun question. One last question to ask you here. Yeah, circle of, so r equals negative 6 would be a circle of what radius? We got an answer in chat already. Nick says it's the same thing. Good, yeah, circle centered at the origin of radius 6. It's just as you put your points together, they'll all be reflected through the pole. So like if you had negative 6 comma negative pi, that would be the same as 6 comma pi. You'd reflect each point through the origin. It's not hard to see. Okay, so these are two nice families of functions to look at. R equals a constant and theta equals a constant, but they're not the only ones we want to look at. Indeed, most of the functions we want to play with are a little bit more challenging. So before I let you guys go today, I need you to start trying to grapple with this challenge. Here's the new challenge. Take a graph in Cartesian coordinates and translate it into polar coordinates. And I'd like to start with something simple. One plus cos theta. So in Cartesian coordinates, and anytime you're trying to graph a more complicated polar function, this is indeed a polar function here, right? R is some function of theta. First, you graph it in Cartesian coordinates, graph it in regular rectangular coordinates. You're going to use that graph, its shape, its increasing, decreasing, all the good shit about it, to help you come up with a good polar graph. Rather than just going point by point by point. With these more complicated graphs, you need to be thinking about the shape of the graph in the Cartesian coordinates to help you understand what to do in the polar coordinates, because it's a fairly tricky procedure. So first, the Cartesian graph. Cos theta bumped up 1, right? That's what this looks like. So here's the theta axis. Here's the r axis. I'm graphing this in Cartesian coordinates. Here's 1, here's 2, down here is 0. Thanks. I'm going to draw in a dotted line at 1 because that's like my new equilibrium. I'm taking my cosine wave and bumping it up by 1. And then cos, you remember what cos looks like. Let me mark off some things. You always want to make sure you go out at least to 2 pi, regardless of the period. So most of the functions we'll be graphing here will be periodic functions. And regardless of the period of the function, you always want to go at least out to 2 pi, because I want to know what happens when you rotate all the way around the polar coordinate system. So that's pi, here's pi over 2. Here's 3 pi over 2, roughly. All right, so I know that if I plugged in pi over 2, the cosine would be 0, and I would just get 1. This is 1, 2. I know the cos of pi is -1, so I'll be down here at 0. I know the cos of 3 pi over 2 is 0 again, so I'll be back here at 1. I know the cos of 2 pi is 1, so I'll be up here at 2. So here's my cosine wave. Maybe I'll go back to doing the graph in red. Oh, Hamlet, that is a stinky fart, buddy. The dog just ripped the nastiest bit of ass. All right. Here is 1 plus cos theta graphed in in rectangular coordinates on the interval 0 to 2 pi, right? And it continues, you know, like this, but I'm not drawing that. Just interested in the 0 to 2 pi interval. Everybody comfortable with where the red graph here came from? Just took my regular cosine graph, shifted it up 1. Now for the tricky biscuit. The tricky biscuit is translating this graph one piece at a time over into polar coordinates. So this is 0, this is the polar points are like r equals 2 here. So this would be the polar coordinate 2, 0. So I know we're not strictly supposed to do this, but I like to start by drawing in a vertical and horizontal axis like this. All right, this point right here this guy, r is equal to 2, theta is equal to 0, right? So r is equal to 2. I'll mark this as like 1, so I'll mark this as like 2. Here's the polar point 2, 0. Now, as theta increases from 0 to pi over 2, r is decreasing from 2 down to 1. I'll say that again. As theta increases from 0 to pi over 2, r is decreasing from 0 to 1. So here is the polar point where r is 1 and theta is pi over 2. Imagine there's a little arm starting to rotate around like this, and that there's a little guy on the arm holding a little paintbrush. He's standing out here right now, but as this arm starts to rotate, my little fella starts running in. He starts out here and he runs in, and he's like, help me. Well, if I rotated just a little bit and he's run in just a little bit, then I would be like, you know, like here. So you rotate just a little bit, my guys run in just a little bit. Rotate a little bit more, my guys run in just a little bit more. So maybe he would be like here. And we know that this pattern needs to continue to here. So as theta moves from 0 to pi over 4, r is decreasing. My little guy is running in along this arm until we get up here to pi over 2. Now as we rotate past pi over 2, r is still decreasing. And by the time we get to pi over here, it's going to be 0. So again, I want you to picture the intersection of the line and this pencil as a little guy running back and forth on the pencil as the pencil rotates around. The distance from my hand to where that line intersects the pencil, that is r, right? So here r is 2. R is decreasing, 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 r is 1. R needs to continue decreasing as we spin around until we get to pi. So imagine now that r continues to decrease. My little guy is running in. He's at the origin. What's that going to look like? It's going to look like this. So the bits of the graph we have so far correspond to these bits of the rectangular graph. Again, think about the little guy running around on the pencil. He's running in, still running in, running in, running in, running in, running in, running in, running in further, running in, running in, running in, running in, running in, running in. He's at 0. Make sense? I've been looking for a good animation to describe this. I may use PyMath to make one day, but I still haven't seen a good one out there. So I don't really have a good animated GIF to show you here. But this is where we're at. Now, as I continue rotating past pi, like this, I should be able to think about my guy. I should be able to think about my guy running around again. What's going to happen? As I rotate past pi, if I look a little bit past here, then my guy should start to run out again because r is coming back out. Now r is increasing. So everywhere here on this graph, my guy is going to be moving out along this arm. When we get to 3 pi over 2, we should be at radius 1 again. So 3 pi over 2 is here, radius 1 is here. So what we end up doing is producing actually a neat little symmetric piece here. And then as we rotate more and more and more and more, we come in like this, tangent there. So this graph is what we get from this fellow. And I know it takes some practice to see. So this is the polar point. We started at 2, 0. Here as theta increased, r was coming in. So as we rotated around, the little dude's running in, running in, running in. And he continues running in, running in, running in, running in until we get to 0 at pi. So right here, this was the polar point 1, pi over 2. We came into the pole here. This is the point 0, pi, polar point 0, pi. And then as we came past pi, r poked back out to become positive. Here we were at 3 pi over 2, 1 again. I'm sorry, 1, 3 pi over 2. R always comes first. All right, can we kind of see it? And then here we landed at 2, 2 pi. It takes some practice. I can try to show you in Desmos a little bit. They do have a polar coordinate system. Yeah, I mean, it's okay. But I don't know if I'll be able to show it as nicely as I'd like. Yeah, here we go. But I would love if I could get a slider. See what we got here. It's a little bit tricky. Whoa, that's pretty wild. All right, let's hold the phone. Yeah, here they're doing something very, very different. They're letting us look at areas in polar coordinates. That's not what we want, though. We'll have an idea. Rather than doing it like that, let me look at a few more simple examples. We'll stick to pencil and paper. Pencil and paper is fine. I don't have something prepared for you. So let's look at another kind of easy example. That one wasn't super easy, but it wasn't super hard. Another example here. Let's just try graphing r equals theta. We haven't done that. So here the Cartesian graph. You know, this is the same as like saying I want to graph y equals x, right? It's going to look like this. This is your theta axis. This is your r axis. So points along here are like, you know, pi over 4, pi over 4, and 2, 2, and what would this be? This would be like negative pi over 2, negative pi over 2. And if we want to try to translate this guy to polar coordinates, Let me just go from 0 to 2 pi. So maybe here is pi comma pi. No, here would be 2 pi comma 2 pi. So we can think about, here I'll just let theta run from like 0 to 2 pi to start. Of course, when r is 0 and theta is 0, we're at the origin. If I let theta increase a little bit, r will increase a little bit also. So maybe I'll mark this as like 1, this is like 2, this is like 3. So pi over 4 comma pi over 4, if I come out pi over 4, that's a fourth of the way to pi. Pi is like right here. That would be like here, maybe here. Yeah, here. And then I'd rotate up by pi over 4. So it's like this. So here's the polar point pi over 4, comma pi over 4. And then as I move a little bit further along out here, maybe here I have, let me do this as pi over 2 comma pi over 2 to make it easier to understand. Pi over 2 is halfway to pi. That's like here. So we would be like here, where the angle and radius are both pi over 2. And then out here, I'd be at pi comma pi. So that pi is like this distance. And then by the time we're down here, we'd be at like 3 pi over 2 comma 3 pi over 2. That's 1.5 times this distance. That's already getting a little bit too big for me to draw. Let me do. Okay, so if you start connecting these dots, what kind of object do you notice here? What kind of shape is this going to have? Yeah, it's a spiral. By the time theta got to 2 pi, which would have me back along my polar axis here, I'd have to go all the way out to r equals 2 pi. That would be like out here. So my spiral would continue around like this, and then so on. It's a special kind of spiral. It's actually called an Archimedean spiral. Let me get out of this. This is silly. If you don't believe me, here it is. And they're going from 0 to 12 pi. I mean, quite a lot more than I needed. We can just look 0 to 2 pi if we want. There it is. And you see it starts off, just like our picture. Yeah, this is called an Archimedean spiral. And you can form lots of spirals like this. You could do theta over 2, and that'll bring it in a little bit. You can go 2 theta, that'll bring it out a little bit. Some fun ones are natural log of theta, or e to the theta. E to the theta is cool. This is called a logarithmic spiral. And it's kind of similar to that golden ratio spiral that people fetishize for whatever reason. Their personal philosophy tells them to. So yeah, this is fun. any monotone increasing function of theta can go here and we'll produce a spiral. But let's get back to graphing trig functions, right? Trig functions are the things that are sort of most exciting. I just wanted to show you one more example where it's kind of easy. All right. What am I doing on time? We've got time for one more slightly challenging example, and this is where I'll leave it for today. On Wednesday, I'm going to show you how to do calculus operations in polar coordinates, specifically how to find like areas. So what about good old-fashioned sine theta? Where the fuck this camera hates me. All right. I begin with the Cartesian graph. And always at least from 0 to 2 pi. We'll mark this as 2 pi. Pi. 2. 3 pi over 2. I'll come up here and mark this as 1. Come down here and mark this as -1. You know the sine of 0 is 0, the sine of pi over 2 is 1, the sine of pi is 0, the sine of 3 pi over 2 is -1, and the sine of 2 pi is 0 again. So the sine wave here is very simple. It looks like this. So what is the polar plot look like? We're going to have to imagine that arm rotating around from 0 radians all the way to 2 pi radians. So I have to think about this arm spinning all the way around and imagine what my guy running in and out on that arm is going to do. The trick here is that sometimes this is negative. And you know that when r, the radius, is negative, things in polar land can get a little bit wonky. So this is where these things can get hard. Now we know we're starting at 0, 0. And then by the time we rotate from 0 up to pi over 2, we've come out to 1. So let me mark this here as radius 1 on my polar axis. And by the time we've come up to pi over 2, we're here. So we started here. And if I were to rotate just a little bit forwards, that means I'm looking at just like this little piece of the graph here. Then r will have gone from 0 up to something a little bit positive. So if I rotate out just a little bit, then r will have come out just a little bit. If I rotated out just a little bit more, I know that r will have come out just a little bit more and a little bit more until we get up to here. So I've got something kind of like this going on. Pardon my bad art. So up here, this is the polar point, 1 comma pi over 2. And theta is pi over 2, r is 1. If you want, you can insert this point here, which should be like where theta is pi over 4. The sine of pi over 4 is root 2 over 2. So it would be root 2 over 2 comma pi over 4. And then as we rotate back here past pi over 2, r starts coming in. So the little guy on my thing here is going to start running back in. And that's going to trace something like this. And by the time I get to pi, he's come all the way in. Now, as I rotate past pi, right, so as I come in, look at where this is intersecting my thing. R is getting smaller, R is getting smaller, 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 smaller. Here at pi, R is 0. If I come past pi just a little bit, R should be poking out here, except it's negative, so it's going to be reflected. So what happens is as we go through this part, we're actually going to trace this part of the circle again. Even though my arm is down here, and I should be drawing in quadrant 3 because R is negative, I'm actually reflected through the origin up here, drawing in quadrant 1 again. When we get to 3 pi over 2, where my arm is pointing straight down, right, R is negative 1. So you go to 1 comma 3 pi over 2 and then reflect through the origin, and that takes you back up here. So this is the same as the point negative 1, 3 pi over 2 that we get right here. This business with the radius being negative is sort of the hardest thing to get comfy with. And it's the thing you're going to need to practice the most. You're also going to want to kind of develop a library in your head, just like you know y equals x squared is a parabola, you know x squared plus y squared equals 1 is a circle. You want to know that r equals sine theta is a circle. Same is true for r equals cos theta. So let me show you some resources in the textbook where you can fiddle and get a little more comfortable. Ooh, I must have closed all that. All right. Here it is. So there are some things that are just nice to know. So here they have a fairly nice sort of explanation of the shape that we drew earlier. By the way, these are called cardioids, the kind of heart-shaped thing that we drew first. I think I did 1 plus cos theta with you guys. If you do 1 plus sine theta, it looks like this. It's worth spending the time to go through these examples on your own. I don't necessarily recommend worrying about any of these more complicated guys, but there is a table of sort of commonly used ones. We're not going to talk about tangents. Tangents are boring here. Do I not have it? Graphing. No. Yeah, let's see. Here we go. So here's a family of curves, 1 plus c sine theta, where they let c go over a few particular values. This actually isn't what I was looking for. I thought they had kind of index here. So what I'll say is that to graph a function in polar coordinates, first graph it in Cartesian coordinates. And then you have to translate the graph over little bits at a time. I might be thinking of the pre-calc text that actually has that table of different shapes. Next time, I'm going to show you a few other special shapes, a few other special polar graphs, right? There's some that we've looked at here, that r equals constant, theta equals a constant. This is r equals 2 cos theta. It's a circle of radius 2 centered at the point 2 comma 0. Here's 1 plus sine theta, it's that cardioid. And these are called petal graphs. So I'm not going to beat you to death, but I do want you to practice. And I've given you a few of these in your homework. You're welcome to use Desmos to play around, but just make sure you also spend some time graphing them by hand. So we can fiddle like 2 sine theta. I'm having such a hard time there because I'm zoomed out so far. They get interesting when you allow the functions to be sometimes positive, sometimes negative. You can get self-intersection. This is kind of like a cardioid, but with an inner loop. The inner loop here is coming from the theta values that correspond to negative r's. another fun family of curves here are these petal graphs, like cos 2 theta is looking kind of like a flower with 4 petals. So you might think, oh, well, cos 3 theta then probably has 6 petals, right? But it doesn't, it just has 3. Cos 4 theta is going to have 8 petals. Cos 5 theta just has 5. So there's some interesting patterns here. You can compare how these graphs look with the parameters that you can fiddle with. If you swap a cosine for a sine, what does that do? You know, cosine and sine are out of phase by 90 degrees. So I'd expect these graphs to be similar, just out of phase by 90 degrees. So fun things, fun games you can play. I encourage you guys to play them. Get working on that last WebAssign assignment and make sure you write your solutions as you go. I'm not expecting perfect, neat, clean solutions because this is longer than your other study guides. So just remember that this last assignment in WebAssign is sort of doing double duty. It's your last homework and it's also your last study guide. I'm not going to hold you to the same standards of neatness that I do for the other study guides because they were shorter. But in order to get credit for the study guide, you still need to scan the work and submit it in Canvas. That's necessary. So please don't forget to do that. Okay. Wednesday, we're going to talk about calculus in polar coordinates. And then Friday is going to be your test. Now, as promised, the test will go very, very easy on polar coordinate stuff. It'll be mostly power series, arc length, surface area. And then the final, I will test you more aggressively on things like parametric curves and polar coordinates. So Friday's test will have a little bit of the parametric curve and a little bit of the polar coordinate stuff, but for the most part, it will be power series and the chapter 8 stuff, surface area, arc length. Any questions for me before I let you guys go today? All right, I'll look for a good animation describing what I was talking about, that sort of rotating arm thing to help you guys see what's going on here. But that is it then. I'll see y'all on Wednesday, unless you want to come by office hours. I hope everybody has a lovely rest of your day. Yeah, take care.